All right, so these notes are covering section 2 of chapter 5 in chemistry. Again, we're continuing talking about the periodic table, some different things that you're supposed to be able to look for and see. So there's a relationship between electrons and its sublevels and the length of each period. We talked about that last section. But we're also going to be able to talk about those 4 different blocks. Again, there's 4 sublevels, S, P, D, and F. We should already know that. And talk about how that works. And then we're going to talk about group configurations and group numbers. And then we're going to describe locations on the periodic table and the general properties of different kinds of elements, right? So some of those groups have names like alkali metals or halogens. Some of them don't really say that. Like we'll talk about maybe the nitrogen family. It doesn't have a special name, that group, because nitrogen and phosphorus are actually a lot different than bismuth and moscovium that would be down at the bottom there. And arsenic and antimony are different than those things, right? Because as long as you're in that area of the periodic table where the stair step exists, you have some metals and nonmetals in that same group, so we can't just call them all the same thing, right? That's why they don't have a name for the carbon, nitrogen, or oxygen family. Whereas the whole column that includes fluorine, they're all similar to each other, right? So we call them all halogens. Should be pretty simple when it's all said and done. So we're going to run down a few things real quick. Right, again, electron configuration, that's where we get our period, that row, that shell of electrons that we talk about, right? When we get to the end of the period, we have a noble gas always, right? And that means we have a full shell. And the length of the period is dependent on the number of electrons needed to fill those sublevels that may or may not exist, depending on which shell you're in. So again, when we did Aufbau principle last chapter, and we talked about 1s, 2s, 2p, right? The first shell holds a different number of electrons than the second shell, right? So we have those problems. But we also learned a lot about where we were in the periodic table and exactly what we were filling at any given time. So really we're just reviewing and reiterating some of those things, and hopefully it just makes more and more sense, right? Because that third energy level may have the ability to fill some d orbitals, but those don't get filled until after I enter that 4th row, so that gets a little bit confusing. That offset is going to be a problem. But you definitely already should be able to label the S, P, D, and F blocks on your periodic table, because otherwise I have no idea how you would have finished any of that electron configuration from last chapter. So should be pretty much reviewed there, right? Otherwise, this stuff here, when I say main group, make sure that you recognize them, maybe even in your notes, that S and P are both part of this main group. So I'm going to be talking about the S block here for a second when I talk about group 1, when I talk about group 2, and even these special cases, hydrogen and helium. But P block is also in main group. So that's like on the back of your notes. That's on the back page when you flip it over. So I would like flip it over right now before we talk about these things, maybe put a little divider right here and make sure that you know that all of the things up to this point are main group. Because otherwise I've had students in the past that thought that just S block was main group, because you know that's what was under it on the front of the page. But S and P are both main group elements, so you need to know that. Make sure that that's emphasized right away. Otherwise, a lot of this other stuff is review, like I said. Like you might not know that name alkali metal for group 1, but lithium, sodium, potassium, rubidium, cesium, they all have similar properties, and they're all right in the same group for a reason. They're all represented generically as NS1 because they all have 1 electron in that S sublevel, right? What we're going to do with this information, that NS1, is you're going to have to be able to understand that, okay, if I wanted you to find potassium quickly, I might prefer to say 4S1 over potassium because I know you could find it quicker that way, right? So you have to be able to, depending on what I say, maybe I'll say 5S1, look at your periodic table and find out what that element is. So if you looked quickly, you should be able to tell that that's actually my rubidium, number 37, And again, it's just what we did last chapter, so it should be pretty easy to do that, right? If you can't do that, that would be a problem for sure. So n could be any value from 1 to 7, right? But more specifically, if I say 4s1, I mean potassium. If I said 3s1, I mean sodium, right? All of these elements are silvery and soft, right? Silvery shouldn't be a surprise because that's what a lot of metals look like, but the soft is a little bit weird, right? If I had a solid metal in front of me, usually I think of that being hard and rigid, right? But these metals, if you could find them in that form in a solid state like that, they would actually be very soft. You could cut through them with a butter knife, like they're butter, right? But they'd look like a metal. They'd be silvery, shiny, right? So it's a little bit weird. But that being said, these things are so reactive, they're very, very reactive, that you're not going to find them free in nature. So add that into your notes right here. They're not found free in nature, meaning the only way you're going to find these things is if they're already in a compound like sodium chloride that you're familiar with, salt, right? If you look at salt, it's not silvery, shiny, right? It doesn't look like a metal, but there is a metal in that compound, right? But like I said, sodium doesn't exist in that silvery, solid state unless I make it exist that way, right? We can obtain these things and make them in the lab. It's very hard to do because they don't want to be like that. In fact, if you do make one of these samples, you have to store it in kerosene to protect it from the water that's in the air that we're breathing right now so that it doesn't react and just turn right back into what it was to begin with, right? So they're super reactive with water. We might watch a video on that later. You can look up one if you'd like, right? Look up how alkali metals react with water. It's pretty explosive, actually, right? But when it's all said and done, they all have similar properties for a reason. They all have this one electron in that outermost shell, which is actually what makes them really reactive to begin with. They don't want that electron. They'd be a lot more stable if they could just get rid of it. Because if they got rid of it, they would have the same configuration as a noble gas, right? So you'll see the elements in group 1 are super reactive. Elements in group 2 are also pretty reactive. They also, in these notes here, say that they are too reactive to be found free in nature. Same thing, they'll react with water pretty easily. So you're always going to find them in like an ionic compound like a calcium carbonate, which you know more commonly referred to as like chalk, right? But when it's all said and done, alkaline earth metals, they have 2 electrons in that S sublevel. So again, I could identify them, any of them, with like a 3s2. That obviously would be a magnesium atom, right? I could say 6s2. You might have to look up what it is, but if you find it, that's barium, right? So be able to do the same thing we did with group 1, group 1 as we are here with group 2. If I say 1s2, it can be kind of confusing because there's a hole there, right? But there's a hole there because helium usually isn't at the top of that group. It's usually moved all the way over here to go with the noble gases. If I click on properties, it'll move right back over there, right? But helium technically is 2s2, but as you can see below, helium and hydrogen are kind of their own deal, right? So if I look down here, hydrogen's kind of unique. It doesn't really fit well with any group because it actually can act like a metal or a non-metal, right? So even though it's in the same group as lithium, sodium, potassium, rubidium, it's not really going to do the same things, right? And it's not going to do the same things because it's different, right? Since there's only that S sublevel for hydrogen, so normally it would be a 1s1, 1 electron in that orbital, right? It has options, right? Sometimes hydrogen likes to lose that electron and get a charge, right? End up with a positive charge. Sometimes hydrogen would prefer to, let me change that up a little bit, gain an electron, right? Add a new electron here, it would look like helium, and helium's super stable, right? So if it could get to that 1s2, that'd be good as well. and then it would have a negative charge, right? And really, a lot of the time, hydrogen doesn't end up with a negative charge. It just matches up with some other element that would also like to gain an electron. So if I have one free electron here and one free electron here from the hydrogen and the oxygen, they could share those two electrons and make a bond, right? We've talked about covalent bonds before. So hydrogen's just unique because it can do whatever it wants to do. It's the most flexible element on the periodic table. It can act like a metal or it can act like a nonmetal. Just depends on what conditions you put it in. Otherwise, helium again is weird because it's super stable, right? Since technically its shell is full, right, with 2 electrons in S, it's going to be considered a noble gas, and that's why it gets moved over to be with those noble gases in your typical periodic table. But that being said, it still belongs in the S block, technically, right? So don't get too confused by that. If I get to the P block, again, this one has a lot of different properties because carbon's different than nitrogen and oxygen and fluorine, right? So there's many elements in that whole block, right? Just like there were 2 different kinds of elements in our S block, you have 6 over in the P block. Now when it says NS2, NP1 through 6, right, just understand that what I mean is, okay, I have 2S2 and then I have 2P5, right? Same as before, I should be able to find out what element that is, right? 5, if I'm 5 electrons into 2P, that should be fluorine, right? So you should be able to do this. Most of the time, this information is kind of useless. You're really just looking at the 2P5 and finding what you need to know. But sometimes I can try and trick you, like on your last test, because I could do 2S1, 2P3, and although you might think that you're supposed to go 3 into P right now, 2S1, 2P3 is not nitrogen, right? 2S1, 2P3 was actually carbon, right? That last question on your last test. It's a weird carbon, because again, if it's 2S1, 2P3, that means there's 1 electron in S and there's 3 electrons in P, and there was actually supposed to be 2 in S before I even started filling P, right? So what happens in these situations is you just have to understand that, okay, if this is not a 2, I have to make it a 2 to figure out what element this is, right? But if I make this a 2, this also turns into a 2 because I had to take one of these electrons and move it over here, right? So most of the time, the 2s2, the 3s2, the 4s2, that's just going to be useless information, because as long as I say 4s2, then you can just go straight to the 4p look that I'm giving you. And if it's 4p2, then it's probably going to be germanium here, right? There's no real other option for it. So, but if it's at 4s1, 4p2, then I actually would be talking about gallium, right? But gallium doesn't necessarily do that. I could only do that if it's a special case like carbon was. So again, be able to identify elements easily and go find them based on that label that I give them. Again, NP6, that's kind of a special group because those noble gases have full shells. That's actually what makes them the end of a period, and you have to start a new row for a reason. Again, there are metals, nonmetals, and metalloids. That's why there's only one group with a special name that's not the noble gases, those halogens that are fluorine, chlorine, bromine, iodine. But the other groups, right, usually they're just called families, like the oxygen family, the carbon family. But you can't really have a group name for carbon's family because carbon's way different than tin and lead, right? Tin and lead are metals, carbon's a non-metal. They're going to do completely different things. So again, stair step comes into play, right? You guys should know what I'm talking about when I say that. But when you cross that stair step, the ones top right are non-metals, bottom left are metals. They're going to have different properties. Halogens, again, they're special. What makes them special is that they're very, very close to being full, right? if you have fluorine, it's going to be, again, 2s2 2p5, as I said above. And that would mean that you got a full S and that you have 3 orbitals in P that are very nearly full. I'm 1 electron away from being just like neon, from being happy and stable like neon. So fluorine will do about anything in its power to gain an electron to get to that point, which is why they are the most reactive nonmetals. Fluorine is the most reactive nonmetal, but fluorine, chlorine, bromine, and iodine are among the most reactive nonmetals for a reason. There's 1 electron short of being a noble gas, so they're going to do about anything they can to get it. Transition metals, right? I don't really need you guys to know the properties of these so much because a lot of these things are not going to be common every day. Things like these elements are not necessarily in a lot of the common everyday things that you talk about. Some of them are because, iron's in there, copper's in there, gold, silver, but otherwise there's a vast majority of them that aren't really going to pop up in compounds that we deal with in the future, so we don't really worry about them that much. But this is where things get complicated because, as you can see with this little shorthand, NS 0 through 2, N-1, D 1 through 10, this gets pretty complicated pretty fast, right? So I think I have to at least start out with a 4 for N. But if I had 4s2 and then N-1, 4 minus 1 is 3, that's all it's saying. And we know that 3D follows 4s, so that shouldn't be a problem. That was last chapter. But let's say it's 3D6. You could look at your periodic table again, and you could definitely find that. 4s2, 3D6, so I count 6 in here, and that would be iron that I'm dealing with. So same thing as before and same problems as before, right? It's not going to pop up very frequently until you get to the D block, but just like I said could happen with carbon, I might have a situation like this where it doesn't say S2 and then it'll say 4D10 in this case, and you have to recognize that, okay, it said 4D10, but I'm not actually talking about cadmium right now. Because if it's only 5s1, I stole one of those electrons to fill D. That means that I'm really looking at silver in this case. So I have to do that adjustment like I talked about before. It should be relatively simple. You take 1 electron to fill this from D. So this is the actual way to find it on the periodic table, but silver happens to be kind of weird. It probably would prefer to have that extra electron in D to fill D to make it more stable. So we talked about that last chapter for a reason. There are a lot of exceptions that you're going to have to deal with in the D block. So a lot of different elements will do what we're talking about here. You just have to be able to pay attention and focus on the details, because if I say 6s2, then you can ignore it. But if I say 6s0, you better pay attention, because when I say 5d10 in this case, it's not really 5d10, it's 5d8. So when I look down here, 5d8 would be platinum, right? Now platinum is usually going to look 6s0, 5d10, because that would be more stable, right? Or maybe it will, maybe it won't, right? Because actually if I go and check on that with my electron configuration, pretty sure platinum doesn't do that. In fact, platinum does something even weirder. It puts 1 electron over here in D to become a 9, leaves one of the electrons in S. Palladium above it makes more sense. It fills D and empties that 5s so that it can be more stable, right? But again, I'm not asking you to memorize these things. I'm just asking you, when I give you that notation, when I give you anything besides an S2, you have to recognize that and deal with it. So again, the trick is to look at it like, okay, this is supposed to be a 2, so I have to change this to an 8 accordingly. And then I can find it easier. 5d8's easy to find. But you might be fooled and think that it's really 5d10 because you're not paying attention. That's the point. So elements like palladium, platinum, gold are very unreactive and are among the least reactive of all elements aside from your noble gases. They're not reactive for a reason, right? Platinum is this one we just talked about here, right? It doesn't do the S0D10 technically, but something about S1D9 seems to be very helpful for it, right? It has a low enough energy that it doesn't really want to react with any other element to gain stability because it already figures it's pretty stable. Whereas the palladium makes a lot more sense right above it, right? That's the 5S0 4D10. Palladium actually has a full 1, 2, 3, 4, right? It's got full shells all the way through 4D10. So it's going to be really, really stable for a reason, right? Now, gold's on this list too, and gold is a precious metal, right? And gold also happens to be expensive, just like platinum and palladium, right? But what makes them expensive is not necessarily their abundance, right? That there's not that much gold, that's true. But the reason why gold is so much more valuable than other metals is because it's so unreactive that it lasts the test of time. It doesn't change over time, right? So that's what makes it special. That's why there might be gold plating on the end of your USB plug and or like an HDMI cord so that it doesn't rust and then it doesn't stop working over time, right? It'll still do the same thing it's done from the get-go. You don't have to buy new ones constantly. F block, again, we've done these before as well, so I can't really throw too many curveballs here because I've already thrown the curveball, right? If you're still not catching it, that might be a problem because I'm still going to do the same things I did before. If I start with 6S2, I should be followed by 5D1 because, again, lanthanum is weird, right? It's actually in the D block as far as we're concerned. And then I'll do 4F3, and when you go look for that, that happens to be an element neodymium, and you just have to be able to figure out where you're at. But that's the exact same thing we did last chapter. So if you're really having trouble with that, that's a problem, obviously, but that's a problem you've had for a while, right? So hopefully you're picking up on things and catching up quickly because we can't just stay in the same place forever. The only reason I might have a 0 here for my D is if I could achieve or accomplish something for F, right? You can imagine possibly how this might be stable, right? If I had a 7S2, I'm still going to write my 5D, but it might be a 0, which actually would just make this normal. 7S2 is supposed to be followed by 5F on my off-bow principle. But the only reason that I might end up with no electrons in D is if maybe I can accomplish something in F, right? Remember, F can hold 14 electrons. So 7 is half of 14. I can spread those electrons out in one sublevel, not needing two sublevels, and maybe that could make it a little bit more stable, right? I definitely would do that if it was a situation like this, right? 7S2, 5D1, 5F13. You can imagine how it would probably be much better for this to be a 0 and for this to be a 14, because then I can fill that F sublevel, right? Now, excuse me, on both of those, I had the wrong number here for D, so maybe I should fix that real quick. Sorry if that was confusing you. These were supposed to be 6D in both cases, but, you know, I make mistakes. So recognize that you might see something that doesn't have that D1, but if it doesn't, it's for a reason. But you were supposed to always use D1, and so that shouldn't be something that's completely off the wall right now. That actually should make sense. All right, so that's all we needed for the video anyway. Sorry about the bell.